And why it was also turned down? Because in 1973, power electronics, and I saw also this paper, was given a keynote speech at Caltech by a fellow named engineer Bill Newell at Westinghouse. I think shortly after that, a year or two after that, he died. Actually, Bill Newell Power Electronics Award was established in his name, and it's still going on as one of the IEEE Society Awards. And here is this diagram. This field existed separate. Power, starting by power, you already mean 60 hertz. Magnetics, you need motors and generators. That's what we mean by power in electrical engineering. Electronics, it's no power. It's signal processing. Control is totally different field. But this is interdisciplinary field, which requires all three. And what is tying these together is they're not at 60 hertz anymore. They're at 60 hertz, and now they progress it to megahertz. And they're going to 6 megahertz. Not that I subscribe to it, and I'll tell you I'm very much against it, because we can do everything at 50 kilohertz, but that's as it is. So now there is all of these things together have to be done to produce products. So, and surely there was a need for a university there, because even control system people, there was a rather special problem how to control and model this switching converter system. Inductors, capacitors, switches, operating in a repetitive fashion, how do you come up with a simple circuit or models? So here, in 74 to 76, as a part of my thesis, I did a new method, what's called now state space averaging, as it's considered one of the standard methods. Here, in the process of that, I invented what's called a Chu converter. You can go to a web page and find 90,000 references to it in books, etc. But anyway, the key to that was new type of a converter, which was one of the 4 basic converters, which I used actually a vehicle to develop this method, because it had a capacitive energy transfer. You see this one in red. In addition to all the conversion methods up to now, used switches, inductors, and transformers. For some reason, they ignored capacitors. And in fact, that is a problem why we ran into some limitations of current power electronics technology, AC to DC converters, DC, as I show up a little later, that we ignored capacitors. We ignored Faraday. Capacitors are named in his name, and why? But here it is. If you want to find out if connection of switches, inductors and capacitor, repetitive switch results in a DC to DC conversion, then what you need to do is establish the method. So what is the method? Look at the flux balance on 2 inductances, and look at the current balance, charge balance on a capacitor. 3 equations, 3 unknowns. You solve them, and you get a DC currents in inductors and DC voltages on capacitors, right? Well, and that's this basis on the state space averaging method. But I went further, because our original contractor, NASA, TRW, gave us a goal. There is a buck boost and a flyback, so we want to model for each one of them, and it's very simple, and you have a computer program, and then you get this whole thing modeled, and you have used it in the future. But what it turns out, that once you make these charge balance and flux balance equations, you turn out very easily that you see that you can find this charge balance, Wolf-Second balance, in such a way that for each position of switch, on time or off time, you have 2 linear circuits. And all you need to do is writing this charge and flux balances, actually meaning using one state of this system and another state, and using duty ratio of the switch as a weighting factor. And you get your state space averaging equations. Once you get that, you get your equilibrium. Once you have equilibrium, as everyone knows in control system, you can perturb it, and you get the AC model. But you know what's interesting about this? I didn't even say, when I write state space equations, I don't even have to say what converter it is. I don't even have to give you a converter. It is given general for any converter, whatever it is, even those which don't exist. Okay? That's nice, because then we gave them a program which was general, and they could get the frequency response model and DC steady state characteristics for any converter. Actually, it's even better than that. You know why? Because you can even imagine that you now try to put some switching configuration that nobody invented before, and then apply this program. And you know what? This program for a DC steady state will tell you these equations in steady state are simple in our equation. If these equations have a unique solution, that converter exists. It has a steady state. If it doesn't, that converter doesn't exist. And what we went further, and that's what university is good about. Look at the general problems, how to define a general problem and solve it. Nobody even asked for it in industry for it, okay? So now, once we have the general program, got a SCAN program, and that was very easy. Just Mac, I think first Apple computer came up in 1977, but we decided very early in 1978 to make a program on IBM PC because we knew that was going to be standard one. We didn't want to maintain two systems. So here was an example of isolated Chuck converter with a couple of inductors that we made a program. I mean, Caltech guys could do anything. So the guy in computer science actually used only 64 kilobytes of memory with the Pascal program to write this graphics-driven program. Even ECADs at the time, you had to give it nodal description. Here, we draw the circuit with the components, and here it comes out. At the end comes out loop gain or frequency response over the whole circuit, okay? One time I had a fun because at a conference, like at a presentation like this, someone asked me, oh, that's great. Before I do that, if you get a frequency response for a given computer, for a given converter, can you enter frequency response and get a converter in the other direction? Well, of course, that problem is not uniquely defined. There are many converters which have the same frequency response, so it's not well defined. But now, where did Caltech really took off with the power electronics? Very early on, we realized that all these power electronics specialist conferences were papers. Professor talking to professor and maybe some of their research students, And what happened is, what was missing is experimental component, missing the place where the people will appreciate the new things. So what we did is, parallel to Power Electronics Conference, it was established a for-profit private conference called PowerCon. And we went to the first PowerCon conference in San Francisco, in Hyatt Regency Hotel. And because we had our students, we couldn't pay for them and for exhibit booths, but we wanted to have exhibit booths. So, what happened? One company gave us half of the exhibit booths, and we put our, charts that we see in the back. We made our own. We made a switching audio amplifier, play your music, and pretty soon my students were really excited talking about it and so on. And there was about 50 or 100 students going to half of that exhibit booth. So the other guy who was owner of the exhibit booth that afternoon, he kicked us out. And he told the owner, I said, why don't you find, I don't want them anymore. Because he volunteered to have us, So the organizer found in the entrance to the room, on the right-hand corner, there were two marble walls, and we just moved our stuff over there, and all these 100 people move over there. So, and pretty soon, the students were excited because they realized we are doing something that nobody in the industry is doing. And there is a job out there for us, Everybody is excited to get that. Right? After I got back, the first thing what happened is Yamaha came the Alltech Lansing speaker company. He said, hey, we wanted to get this Chuck amplifier and went to Caltech patent office. We want to license it, And that's when it dawned on me, wait a minute, why couldn't we make a company to do that and continue making some new innovative products? And Caltech says, why not? And Professor Millerwood and me started a company called Tesla Co. And that's where I worked in a parallel at the Tesla Co. as well as a professor at Caltech for a number of years. This is in 1983 at the exhibit booth of Caltech. This later in San Diego. On the right is my mentor, Professor Millerwood, and I'll talk a little bit more about him later. This is one of our PhD students out of 36 PhD students in General Electric now, I think. So now, move on.